Now we're going to start talking about bonding. And when we're talking about bonding, we're talking about sharing of electrons. In this particular case, we're going to be looking at covalent bonding. Okay? So covalent bonding is sharing of electrons between two nonmetals. And we've seen this before with Lewis structures. We look at water, because we always use water as an example. You've got oxygen and hydrogen and hydrogen. If we looked at the Lewis dot structure, the way that this is constructed, oxygen and hydrogen, each one of them has a single electron, and as we know, those like to bond. So there's a bond, and there's a bond, and what we end up getting is water out of the structure. And the shape of this is bent, that's right, is bent because it's got 4 electronic domains which make a tetrahedral structure. But only 2 of those are counted, so it's going to be a bent structure. So water here is bent because it's going through this covalent sharing. Now what exactly happens with the covalent sharing? So if I've got a hydrogen here, okay, we can look at the hydrogen and say the hydrogen is 1 electron inside of a 1s orbital. Okay? And it's looking to share its electron. If I look at the oxygen looks like this, all right? So, a little circular diagram. But if we look at the structure of it, it's got 6 electrons in the valence, so we have to account for those. So the 2s and the 2p. So we fill up 2 electrons here, 1 electron, and we've got 1 more to fill in, so one of these has to be paired. So that's the 2p. Now if we actually draw the shape of these things, between s and p orbitals, we get an interesting picture. So if I look at oxygen, right, so there's oxygen's center. Let's do it this way. Oxygen has a core, and the core of oxygen is a 2s structure. And it's going to have 3 2p's, right? It's going to have the y, the x, and it's going to have 1 structure coming out here and 1 going behind. And that's the z-axis. So that's the way this thing looks. And if I put in the electrons in this thing, all right, 2 of these orbits have only single electrons. I'll do these 2. And this one will have 2 electrons. And then the S is going to have 2 electrons floating around in it as well. All right? So in order to bond these things, if I get 2 of these hydrogens, the 2 hydrogens are going to come in, and they're going to overlap right here, because hydrogen has 1 electron. Okay, and it's 1s shell. Then the other one that's out here, okay, that's the way it looks. But if you really look at the structure of that thing, it doesn't really match what we see as far as the actual shape of water. We look at something like methane that's got a true tetrahedral structure because it's got nothing but hydrogens around it. It's CH4. Okay, so if I use this example, I'm going to take 2 of these electrons away. I'm going to take 1 of those electrons away, another one over here. So let me put a hydrogen over here, okay, with this single electron. So now I've got 3 of those things paired. And if you think about how hard it's going to be to squeeze a hydrogen, drop a hydrogen in there to share that electron. Okay, that's a really weird shape. So the covalent structure of sharing, okay, let me draw this in, as a matter of fact. For water here, okay, it makes sense as far as filling in the electrons in the actual orbital as for sharing. And let me show you what happens with hydrogen and carbon here. Carbon has one s electron, and I have 3 p's, or I could try to put 2 electrons in the s. Okay, that's actually 2s. And put the hydrogens in to pair all the electrons. Okay, it's kind of wieldy and bulky, and it's not symmetric, and that's a problem because we see things in symmetric in nature, especially when we look at their crystal structures. So let's look at something that may explain this just a little bit better. So what I'm going to represent, all right, if we look at the energy of these levels, okay, and I'm just going to look at the valence of oxygen in this case. Okay, I've got the 1s down here, and it's got 2 electrons in it. And up here I've got the 2p, and that's got the 4 electrons that are in the 2p. Okay? If I were to look at that, I'd say, well, the 1s should fill first, followed by the 2p. But in order to make a true bonding structure, what we can do is we can make sort of hybrid orbitals between the s and the p to make this thing kind of work a little bit better. So what ends up happening is that these guys intermix and hybridize. Oh, I write 1s. Why am I writing 1s? I don't know. I think it's the aliens controlling my brain. Okay, so now we come to this section. All right? What happens when they hybridize? There's energy that's lower than the 2p, but a little bit higher than the 2s. But as a result, I take these orbitals, I mix them all together, and now I have 4 equal orbitals. And since they're of the same energy, it means that their shapes are going to be the same as well. Okay? And if I fill this in with hydrogen, I can put the 2 electrons there. What this means is that oxygen now has 4 sp type orbitals. 1, 2, 3, and 4. And since all these orbitals are equal and of the same energy, they occupy space a lot more efficiently than what we saw with the s and the p. Okay? Now what happens when I mix an s and a p? Here's an S shape. Here's a P shape. I mix these guys up. And what I'm going to end up getting is a hybrid. And that hybrid looks like this. Okay? Kind of looks like a fish, right? And there's a fish, and there's the fins. There's a smoky little face, and here's a tattoo. You know, that type of thing with the fish. Okay? So you've got one tail end, and you've got one larger end. This end out here is really the bonding section, the bonding lobe of this particular sp pairing. But there's 4 of them. So as a result, that's where we see these tetrahedral shapes that we get in our Vesper forms, especially in covalent bonding. So if I look at the shape of oxygen, oxygen has a central nucleus, of course. Okay? And I'm going to have one sp lobe up here, another sp lobe out here. One of the other lobes is going to stretch out, and it's kind of coming at us, okay? Kind of coming out of the board at you. And the other one is kind of going back into the board, okay? So it's going away from us. So oxygen itself has 2 electrons, and 2 electrons in these pairs, and then 1 electron up here. In these bonding orbitals, when they're stuck to hydrogen, okay, overlap quite efficiently and give us those bonds. So instead of having 3 orbitals from P and 1 from S with different shapes and sort of competing a competition for space, they hybridize and give us a more efficient structure. And this is what our crystal structures look like. That's why we know this happens. Okay? So if I look here at methane, and I'm presenting methane in its tetrahedral shape, it's CH4, right? Okay? It's got 4 sp orbitals. So to describe the hybridization, what I look at is combination of the s and the p orbital. And in this case, I've used 3 p orbitals to hybridize this thing because I need 4 orbitals. So I've got 4 boxes here. For carbon, in order to bind with all those hydrogens, I need 1 electron in each one of those. And those correspond to each one of the bonds, right? So the hybridization we end up calling these things is because I use all 3 p orbitals, it's called an sp3 hybridization. Okay? That means that all the hydrogens are going to put 1 electron in each one of these boxes. It should be noted that whenever we have an sp interaction with another sp or an s, we get something called a sigma bond. It's the first interaction. And if I look at this, I see this lobe come out and then the hydrogen overlaps in that particular shape. It's a terrible drawing. But this particular shape, when this overlaps, okay, they overlap and they share electrons very closely, like this. Okay, so they're holding onto the electrons very easily. When that happens, the bond is pretty strong. And this first bond that we get is called a sigma bond. And notice that it's an sp hybrid bond. Okay, in this case, it's s-sp, s from the hydrogen, and sp from the carbon, because it's a hybrid. If I stuck another carbon over here, you'd have an sp-sp overlap to make that sigma bond. Okay? Now, what if I don't use as many p orbitals? That's a good question. There are some cases where you're not going to have everything as a single bond. In some cases, you'll have double bonds. All right? This molecule is called ethene. Okay? Now that I've got a double bond, I look at that and I've got to figure out how I can make 2 bonds occupy the same space. So I've got single bonds, and each one of these single bonds, each one of these is going to be sigma. So it's the same type of overlap there, but that inner structure, that's something that's interesting. If I draw out the carbons here, each one is overlapping with its sp hybrid. Okay? I can't do it again because I've already got electrons in that space and they're going to repel. So I have to make different space for that second bond. Okay? So this is our sigma bond right here. If I make extra space, I have to use my p orbitals in order for that to occur. Okay? So I have to have 1 p orbital on both carbons in order for this type of electron sharing to go. And the electrons kind of move between each in a sharing cloud. And because this only involves the p orbitals, they're called pi bonds. Okay? So this is 1 pi bond. Okay? So what does that look like? So for the hybridization here, I used 3 sp hybrid orbitals. I used 1 sp here, 1 sp there, and 1 sp over here. So I've only had to hybridize 3 of my p orbitals. What I'm left with is going to be sp2, okay? And what this means is I'm going to have 3 sp hybrid orbitals and 1 p orbital, okay? So if I look at this as far as structure goes, these are all my SPs, and this is where my electrons go, and I'm going to have 1 p orbital that still has an electron in it. Okay? This greatly affects the shape of things too. If I have a double bond here, it's considered a single bond. So if I look at the structure, it's gone from tetrahedral to trigonal planar. Okay? All right. One more. Okay. So I've got sp3, sp2. Is it possible to have an sp2 bond? The answer is yes. What I'm going to do is I'm going to take this ethene that I drew earlier and I'm going to change it into acetylene. So with acetylene, I've got a triple bond between the hydrogens, and then single bonds to each one of the hydrogens. Okay? I'm keeping the shape here because I want to show you how this works. So here's the sp orbital overlap over here. Okay? Those are overlapping. But where am I going to put this other p structure? If you can think in 3 dimensions, there's one dimension that has been used. And that's the dimension that's coming out of the board at you. So I've got, at 90 degrees from this other p orbital, another p set of p's that are coming out. Okay? So these electrons are going to share between this other set as well, but behind and in front of this plane. So one, if it's at this end of the board, the other one's 90 degrees in this plane. That's what I see. If I look at it from this angle down, if I look at the carbons that way, what I end up seeing is pi 1 and then pi 2. Okay? All right. So what I end up seeing is this structure. So we call these carbons sp hybridized. So carbon single bonds. Just draw a glue structure here. This is sp3 hybridized. Let's draw it this way so we keep the same color structure. So that's sp3 hybridized. sp2 hybridized is if I have a hydrogen over here and a hydrogen over there, and I've got a double bond to carbon. This is sp2, and sp is a carbon with a triple bond. Okay? It should be noted that other things besides carbon will also hybridize these things as well. So if I see an oxygen with a double bond, that oxygen is going to be sp2 hybridized as well. And if I see a nitrogen, in nitrogen gas, for example, or cyanide, nitrogen with a triple bond and a lone pair, this thing is going to be sp hybridized. The lone pairs in oxygen and nitrogen are also going to occupy, for the most part, sp orbitals as well. So it's okay to have lone pairs in sp orbitals.